We're now going to look at an example of calculating a partial derivative. This is one of the notations that means that we're going to evaluate the partial with respect to x. And if we're evaluating a partial derivative with respect to x, that means that we're going to be holding the y values or the y variables in the equation constant and treating them just like we would treat a regular constant. We can use this kind of partial derivative notation, or we can use a subscript to indicate that this is the partial with respect to x. But either way, let's evaluate this partial derivative by looking at this first term. Now, the y value is being held constant, so is the 2, so the only varying part of this first term is x squared. So we won't be using the product rule, but basically just a constant multiple rule. So since 2 and y are constants, I'm going to pull that out and then just calculate the derivative of x squared with respect to x, which is 2x. Now moving to the next term, again we've got the constant multiple, -3 is the derivative, and since y is being held constant, we treat it the same as we do the 10. So -7y, the derivative of -7y with respect to x is just 0, and the derivative of 10 with respect to x is also 0. So this partial derivative with respect to x turns out to be 4xy minus 3, and that's it. We could also expand this notation a little bit to say, by the way, this partial derivative with respect to x is a function of x and y, and looking at this partial with this functional notation here is going to be helpful as we move through this example. So in part B, we're asked to calculate the first partial derivative evaluated at 1, 2. So that means that we're basically going to be plugging in 1 for x and 2 for y. So this first partial with respect to x evaluated at 1, 2 turns out to be 4 times, we plug in 1 for all the x values and 2 for all the y values, and then -3 is that constant. So we have 8 minus 3, which is 5. Now, in order to determine the meaning of this number, I feel like it's helpful if we look at a graph. So I'm going to go to GeoGebra to help us understand what this partial derivative actually means. So here we are in GeoGebra, and I've already preloaded all of our equations into here. The original surface was here. Z is equal to 2x squared times y minus 3x minus 7y plus 10. I'm going to turn the surface on. It's a little weird looking, right? It's kind of busy. It's hard to really see what's going on here. This is the first octant, right? We've got our positive x-axis, our positive y-axis, and I'm now going to slice this surface with the y is equal to 2 constant y plane. So let me turn off the surface for a second and turn on the slicing plane, and you can see that we are going through the constant y value, y is equal to 2. Now, I'm going to turn the surface back on so you can see that intersection. Again, it is quite busy, so hard to see, but I'm going to rotate around here just to kind of show you what's happening. Let's look at this xz plane, straight on to the xz plane, right? This intersection curve is happening in the y is equal to 2 plane. Again, that's parallel to the xz plane. So this parabola is that curve of intersection that we're getting when we slice it with the y is equal to 2 plane. I'm going to go ahead and just turn on this intersection curve so that you can see that's where the surface and the plane are intersecting. In order to make it easier to see though, I'm going to turn now off the intersecting plane and the surface so that we can focus in just on that curve of intersection. And the ordered triple that's on this curve is going to have a domain element of 1, 2, and then the z value is actually -3. We can determine the z value by plugging 1, 2 into the surface function. So here's the ordered triple that we're interested in with this partial. And I'm going to go ahead and graph the equation of the tangent line. We'll find this equation in the next part of this example. But again, let's take a look down onto the xz plane where the y-axis is coming straight at us. And we can see that the y value, we're not going to get a change in the direction of y, right? Look, we're in the y is equal to 2 plane. There's no change in the direction of y. We're only getting change in the direction of x and in the direction of z. And what this partial derivative that is 5 tells us that the z values are going to have a change in z that is 5 units. So I'm going up 5 units. all the way up to here as my x values change by 1 unit. So for every 5 unit increase in the z, I get a 1 unit increase in the x coordinate. And the partial derivative gives me the slope of this tangent line at this domain element when I'm slicing with a constant plane y is equal to 2. In part C, we've been asked to find the equation of that tangent line, and the tangent line is going to pass through an ordered triple where x is equal to 1, y is equal to 2, and the z coordinate is determined by plugging 1, 2 into the function. Remember, this z value range element is the output of this function with 2 independent variables. So let's go ahead and figure out who is the z value when we plug 1, 2 into this function. So we get 2 times x squared, x is equal to 1, times y, y is equal to 2, minus 3 times x is 1, minus 7 times y is 2, plus 10. And the function evaluated at 1, 2, we have 4 minus 3 minus 14 plus 10. And this is 10 plus 4 is 14 minus 14, cancels everything out, and we're left with just negative 3. So the point on the surface where we're trying to find this tangent line is going to be 1, 2, and negative 3. This is our ordered triple. Now, remember, in order to write the equation of a line in three-dimensional space, we need 2 things. Number 1 is any point that's on that line, and we just actually found one. If we're looking for the equation of the tangent line at this point, we're going to use this point as our point on the line. And the other thing that we need when we're writing the equation of a line in 3D is any vector in the direction of that line. So again, we've already found the ordered triple to be 1, 2, negative 3. Now what we need is a vector in the direction of that line. So let's recall that a moment ago we found that first partial derivative evaluated at 1, 2 to be equal to 5. Now let's consider that from this curly partial notation. So let's recall what this partial derivative actually means. It's representing the change in the range element, or in this case z, with respect to a change in this domain element x. Remember, we've held y constant, so there is no change in y. If we found our partial derivative to be 5, we can write this partial derivative as a fraction. Now, as we saw a moment ago in GeoGebra, we basically are looking for the equation of a pretty steep line that is in a constant y plane. Y is equal to 2 was the slicing plane, so the intersection curve was in the slicing plane. We're looking at about the point 1, 2. My graph isn't awesome here, but that, let's say this is our ordered triple, 1, 2, negative 3. Then our tangent line to this intersection curve is also within that slicing plane. So what we're looking for is a vector in the direction of this tangent line. And the direction vector can be determined by the change in x and the change in z, getting me from the initial point of this vector to the terminal point of this vector. So the vector can be expressed as that change in x. There's no change in y since we're in this constant y plane, and then there's also a change in z. The partial derivative actually gives us that change in z and the change in x that can be used to find the direction vector. So in this case, our direction vector, a vector in the direction of this tangent line, is 1 is the distance that we traveled in the direction of x. There was no change in the direction of y, and 5 was the distance that was traveled in the direction of z, and this is the direction vector that can be used to help us write the equation of this tangent line. Let's also recall that in order to write the equation of a tangent line, we'll use the vector function formula, and I'm going to write sub L here because in the next part of this question we're going to find a vector function for the equation of the intersection curve. So this is the vector function for the line, is going to be an initial position vector plus t, the parameter, times a vector in the direction of that line. So we'll say a vector function that represents this line will turn our initial point into a position vector, say 1, 2, negative 3, and then t times the direction vector, which we found to be 1, 0, 5. We could leave it like this, or we could add these two vectors together to get 1 plus 1t The y component is going to be 2 plus 0t, or just 2, which makes sense because we're in the constant y is equal to 2 plane. And then the z component is going to be negative 3 plus 5t, and this is a vector function for the line that is tangent to the intersection curve at the given point. So now we're being asked to find a vector function for the intersection curve, and of course we are working within the same scenario as we have been for this problem. We have calculated the first partial with respect to x evaluated at 1, 2, and this notation implies that y is being held constant. When we actually plug in values for x and y, not only do we know that this derivative was calculated holding y constant, but we're also able to see what that constant y value is. Because we have a 2 here in this position, it tells us that the slicing plane, the plane that we're slicing this surface with, is y is equal to 2. And if we want to find the curve of intersection that we're looking for is the intersection between the surface and the y is equal to 2 slicing plane. So anytime I want to find where two surfaces intersect, we basically need to plug one of them into the other. We need to merge these two surface equations to get a single equation. In other words, we're going to plug y is equal to 2 into our surface function f at xy. So x is going to continue to be a varying quantity, and of course the z-value output is also going to be a changing quantity. The only thing that we're plugging in as a constant is the 2, so we're going to have 2x squared and plug 2 in for y, minus 3x plugging 2 in for y, and then plus 10. So notice the notation here, this is not a partial derivative, this is a curve of intersection between these two surfaces, and this intersection curve is going to be 4x squared minus 3x, minus 14 plus 10 is minus 4. And this actually makes sense because, as you'll remember from GeoGebra, what we saw when we intersected those two surfaces was a parabola in the y is equal to 2 plane. And we can also think about that as a parabola in a plane that's parallel to the xz plane. And here we see that we only have a changing x and a changing z, so we're in a plane parallel to the xz plane. Now the directions asked us to find a vector function for this curve. And in order to find a vector function, it's easiest to first find a set of parametric equations and then use those parametric equations to create that vector function. So we're looking for parametric equations for this intersection curve within the plane y is equal to 2. One of the easiest ways to parameterize this curve is to just let x be equal to t. The y parametric equation is going to be the constant y is equal to 2 because we're in that y is equal to 2 plane. And then the z parametric equation can be determined simply by plugging t in for each of these x's to get 4t squared minus 3t minus 4. So that vector function would then be t as the x component, 2 as the y component, and then 4t squared minus 3t minus 4 as the z component. So we can take this vector function over into GeoGebra to check. But you could actually use any 3D graphing software. Here is the curve of intersection, and I've put it in already. We had the x component that was t, y is 2, and z is equal to 4t squared minus 3t minus 4. I'm going to turn this intersection curve on, and you can see that that actually is in the same position as where these two surfaces are intersecting. And you can also tell that we have the correct vector function for that intersection curve. Now, let's turn on our ordered triple 1, 2, negative 3. So this was the equation of our tangent line, 1 plus 1t, 2 plus 0t, and negative 3 plus 5t. Now the software changed it to a lambda. I plugged it in as a t, but this is totally fine.